I'm enjoying the conversation, but I guess we have to be on time.
Yeah.
All right, we're live. Please, Greg, go ahead.
Okay. Welcome to the last condensed matter seminar of the semester, at least to the best of my knowledge. It's a pleasure to have Judit Romhanyi from UC Irvine. She's an assistant professor there. She's done a lot of work on strongly correlated systems with an emphasis on topology. So it's a very interesting intersection. She comes from Hungary originally. Did her PhD at the Budapest University of Technology and Economics, and spent some time in Germany, both in Dresden and Stuttgart as a postdoc, and also, I guess, in Japan, working as a staff scientist before coming to the United States. So it's a pleasure to have you, and I look forward to hearing your talk. Thanks so much.
Thank you very much for the kind invitation. It's my pleasure to be here, actually. Thank you so much for for giving me this opportunity to talk about our not so very recent work. So should I try to share the screen? Can I do that? Can I share the screen? Okay, thank you.
Yeah, you should be able to.
All right, thank you very much. So hopefully it's there. Is it okay? Okay. And may I ask if you can see the pointer here?
Yeah, we can see the pointer. It looks great.
Okay, thank you so much. So in this talk, I'm going to, ask this question whether one can have Z2 band topology in the bands of magnetic excitations, and discuss a little bit about the symmetry protection of a specific example that we take, which are triplet excitations in a quantum paramagnet. Okay, so please stop me at any time if you have any questions. I actually wasn't sure about the audience of this seminar, so I think it's going to be, at the beginning, it's going to be very introductory, and then maybe not so much. So please stop me anytime during this talk. Okay, so before I begin, let me thank to my collaborators, Carlo Pence and Nick Shannon. So, and especially to Andreas Thomasen, who was a graduate student back in the day when I was in Okinawa working with Nick Shannon. And what I'm going to present is a big chunk of his graduate research and what you can find in his thesis. So he did a lot of the material that I'm going to present here. Okay, so before I begin, I have to go back to the origins, or somewhat to the origins, and I apologize for showing Haldane's model, because this is probably what everybody is showing when they are introducing non-trivial band topology, and I'm just going to do the same. But I need to to start somewhere and also to put in context our work. So I will just go back to the Haldane's model, and this is and tell you that this is this archetypal model where we can see non-trivial band topology and Chern numbers characterizing the bands of these electrons. That is kind of a starting point for our investigations as well. So the Haldane's model is made for a honeycomb lattice where we have non-interacting electrons that can hop from one side to the other. And if you just had this first neighbor hopping terms, then these bands would be rather boring, and they would not have any kind of topological properties or non-trivial topological properties. But as Haldane pointed out, if we take into account second neighbor hoppings, that due to the symmetry properties of this lattice can have complex amplitude. These are forbidden on the first neighbors because that has an inversion symmetry. But if you have this on the second neighbors, this can actually render the bands topologically non-trivial. And for these bands, when we don't have a touching of these bands, we can compute something that is a topological index, which is in this case the Chern number, the first Chern number, by integrating the Berry curvature over the Brillouin zone. And this is very similar to the Gauss-Bonnet formula, where we have some kind of geometrical shape, and we integrate the local curvature around the closed surface to get the number of the handles in the system, or in this geometrical shape. But instead of the local curvature, we have something that is the Berry curvature that lives in momentum space, and we integrate this over the Brillouin zone. And then we get these numbers +1 or -1, that will, when this is non-zero, then these bands are topologically non-trivial. And in an open system that you can see, with these black lines, we can have also edge modes that are non-trivial that will collapse the gap that we opened, and those are the sign of non-trivial band topology as well. So in experiment, one would see finite Hall conductivity, and this Hall conductivity actually is just related to this topological index. So practically, what we measure is these Chern numbers in this Hall conductivity measurements. Now, if we add spin degrees of freedom to these electrons, then we double the fun, so to speak, and we're going to have 2 copies of the Haldane model. And because the spin up and spin down electrons have opposite Chern numbers, the Chern number is not going to be a good topological index defining these bands, but instead we are going to have a Z2 index, and the Z2 index can be thought of as a spin Chern number, so to speak. It's kind of like a staggered Chern number of these 2 bands that are degenerate with the spin degree of freedom. And we can compute the Z2 index as this spin Chern number, as long as the SZ component of the spin is preserved, as long as it's a good quantum number. And now, instead of just having one edge mode, we have 2 copies of it with the spin index being degenerate, and one of them, they are going in opposite direction. So if one goes to the left, the other goes to the right. Okay, so this is kind of the background that I will need, and just to add to this picture, so what happens when which is going to be kind of the main question for these monetary excitations that I'm going to talk about. So what if we mix the SZ components? What if SZ is not a good quantum number anymore, because maybe we have some kind of a further interaction, such as the Rauschba spin orbit coupling in the case of the Kane and Mele model. But as it turns out, as long as this spin orbit coupling is perturbatively small, so we don't close the gap here between these bands, this Z2 topology is preserved, and these non-trivial edge modes are still going to be present in the gap. But when the Rauschba spin orbit coupling becomes large enough to actually close this gap and drive the system through a band touching transition, then there will be a hybridization between these bands, and also now these bands become topologically trivial, and so are the edge modes as well. So the edge modes are not crossing the bands anymore. And so in this case, one can tell that as long as this time reversal symmetry is present, and as long as the gap remains open, the Z2 band topology is preserved in the system. And now let me move on to the magnets, so the magnetic excitations that we are interested in. So Haldane's model can be actually very simply and elegantly realized in the magnetic insulators. If we just take a very simple ferromagnet, or a magnet or paramagnet that we put in a high magnetic field, then we can, we will have these spin wave excitations that correspond to flipping a spin, which can propagate over the lattice. And mathematically or formally, this is very, very much the same as Haldane's original model, but instead of electrons, we have magnetic excitations that can move around in this lattice, and they would have formally the same, bands that the electrons had. Now we have something like a Heisenberg model, which is the very symmetric, IC2 symmetric model, and this will give us the hopping from between the neighbors here, if we just take the neighboring spins. Then if we add a second neighbor Joushinsky-Morier interaction, so this DM interaction is an antisymmetric interaction, and it's not allowed on bonds which have an inversion center. So the symmetry forbids them. But the second neighbor bonds, they don't have inversion center. So the Joushinsky-Morier interaction is going to be a allowed interaction by the symmetry. And when we write up the linear spin wave theory for this interaction here, then we are going to have these magnons, so this magnetic excitation hopping term that has a complex amplitude, and it actually will play the role of this second neighbor complex hopping in the original Haldane model. So this will render the magnon bands topologically non-trivial and open this gap at the K point. And we will have exactly the same picture as we had for the original Haldane model with Chern full bands, where the Chern number can be computed in an analogous way to the Chern number of the electron bands. So the only difference here is that these are finite energy excitations and they're not fermionic, but they're bosonic particles. So the magnons, they are pretty much featureless objects, and they don't have any charge or anything like that. So we can't expect to see a quantum Hall effect, for example, as an experimental fingerprint. But instead, we can measure thermal Hall effect, which means that we put the sample in some kind of a temperature gradient that will start the flow of the magnons across the sample. And when there is also magnetic field perpendicular to the plane, then these magnons will deflect, and there will be a transverse energy current, which is this thermal Hall effect. And this thermal Hall effect is actually cannot be expected to be quantized because we don't have completely filled electron bands. We have here bands of magnetic excitations that are bosons, and the occupation of these bands is going to be a thermal occupation. So it's not like the whole band is going to be occupied that has a finite Chern number, but just partially occupied. And this thermal Hall response is going to be a temperature dependent response in this case. So the question is, sorry. So here I just show a few of the works that have been done, in this topic, whether we can have, different kind of topological non-trivial bands of magnetic excitations, and this list is not at all complete, and I apologize for that. But there are so many works done in this direction that it's impossible to list all of them here. So it's a relatively new part, like looking for topological non-trivial bands in magnetic excitations, but it's growing really, really fast. And then a natural question is that, so Haldane's model and creating magnetic excitations that have Z topological index seems to be fairly easy and natural, because these anisotropies such as the Jarzynski-Mora anisotropy and so on, they are naturally present in most of the magnets that we study usually. So it's very natural to look for such excitations that have non-trivial band topology. But the question is if we can actually devise a model where we have Z2 band topology, so the analog of the spin Hall effect, or the analog of the Kane and Mele model. And one can ask that, okay, so as I said, flipping a spin or turning a spin down is pretty featureless. It gives us a particle that doesn't have any local degrees of freedom. And then how can we assign a spin to these magnetic excitations? So how can we have a spinful magnon, for example? And the idea is that we can have, instead of just one layer of, say, a ferromagnetically aligned spins, we can take two layers that are each other's time reversal partners. So if the bottom layer, for example, or the top layer has a spin pointing in one direction, then I can couple it to another layer antiferromagnetically that will have a spin configuration in the opposite direction. So this was the first proposal, as far as I know, for these magnetic excitations to realize the Z2 band topology. And in this
case, I ask a question there?
Yes, please.
I mean, are these layers in the model like kind of on top of one another, so there's not a distance between them? Because otherwise it seems like you would need a transformation to move from top layer to bottom layer under like a time reversal. Right. So yeah, exactly. So they are, it's kind of like a bilayer material, for example, that would give you such a... Right. But is it a bilayer with zero separation between the layers, or do you have a finite separation? There's a finite separation. Okay, but then I guess it's not time reversal, because if you reverse time... That's exactly right. Exactly right. So it's not time reversal. That's a very good point. It's time reversal combined with the symmetry of the lattice. And in this paper, what was proposed is that it's time reversal plus a mirror plane that is between these two layers, because time reversal would make the pink to black and so on, and the other way around. But if I also apply some mirror symmetries, then exchanging the layers, so to speak, and then switching the layers and the time reversal operator together will actually leave this model invariant. So
in that sense, it's not a time reversal operator, but it's a pseudo time reversal operator that will leave this model invariant. Is that okay? Sorry. Yes.
Yeah.
Okay. So and that is actually a very good point. Thank you very much for this question, because in the later on in this talk, I will also kind of emphasize that with these magnets, it's not the time reversal symmetry that can have chance to actually preserve this Z2 band topology, but it's some kind of a cooked up symmetry that is a pseudo time reversal symmetry. Right. So what we have here is like, say in the top layer we have the spin up spins, and then the bottom layer we have the spin down spins. And then if I flip this bottom spin, that corresponds to the data as the +1 excitation. And when I flip the top spin, that's the data as the -1 excitation. So in that sense, depending on which excitations I create, whether I flip it in the top or the bottom layer, I can have time reverse partners excitation. And another example is if we, instead of having just these weakly coupled bilayers, we have a bilayer that has a strong interaction between these between the layers. And in fact, if this interaction is stronger than the rest of them, and also is antiferromagnetic, then the ground state for this system can be a quantum paramagnet, which consists of these singlets on these dimers. And in that case, this is actually, maybe more natural to consider, because then I don't have this problem that you were asking, like, okay, so if I apply time reversal symmetry, then what will happen with these layers with respect to each other? So here, it's fine, because the singlet is in that sense, it doesn't really care. And now I have, the local excitations will correspond to breaking up the singlet, and instead of the singlet having an SZ+1 or an SZ-1 triplet, and these triplets are again time reversal partners of each other. So time reversal symmetry would bring one to the other. And then we also have the SZ0 triplet, which is usually not affected by any anisotropic terms, just like the George-Shinsky-Mori interaction, and it just remains the same. So it remains usually topologically trivial, and people usually discuss it separately from the spin-full triplets. And another example what we can have is just, instead of considering a bilayer system, one can consider maybe a single layer system, but that has higher spins, for example, a spin 1. And if you have a spin 1, then we can, if say, for example, we have a strong easy plane anisotropy, then we can maybe realize this as the zero state, as the ground state, and then the +1 and -1, as the +1 and as the -1 states are going to be our local excitations that also have these spin flavors, so to speak, the upspin and the downspin. So these are just a few examples how one can create systems where we have analogous Hamiltonians to the original Kane and Mele model. But there are, of course, differences, and this is what we set out here, is to address these differences and to see whether we really can have a Z2 band topology or not. Okay, so to see in experiments, or like have some similar kind of transverse transport measurement for this system, we can measure magnon speed Nernst effect, which means that we put this sample again in some temperature gradient, and then depending on whether we have an upspin or a downspin excitation, they will deflect in opposite directions, and we will have a spin separation across the sample. So there will be kind of like a spin magnon spin current, or I don't know how to call this, across the sample. Okay, so the question is, so the main problem is that these are, although all of these excitations that we can have that have some kind of a spin degree of freedom, or like an effective spin degree of freedom, these are time reversal partners, but they're not Kramers pairs. So if we write up the time reversal operator for these bosonic excitations, then we are going to have this sigma x matrix and the complex conjugation for them, and this operator squares to +1. So this is not going to protect the Z2 band topology. And the question is if you have anything else that can, instead of this, the usual time reversal symmetry, protect the Z2 band topology. And to answer this question, we investigate a toy model, which is, we took the Kagome lattice, or the bilayer Kagome lattice, but most of our findings actually is applicable for a broader set of magnets. But this is just, this seemed like a good example. So we took this bilayer Kagome system in the limit where the singlets are going to be the ground state. So the singlet covering of the system is the ground state. And we kind of gave a systematic study of this model and tried to figure out like what is the fate of the Z2 band topology. Can we have something similar? Can we have something, like, is there, even if we mix the spins or like these spin up and spin down degrees of freedom, is it the analog of the Rashba term in the Kane and Mele model, or is it something entirely different? So to start this, we just looked at the point group symmetry of this toy model, and starting with this higher symmetry, this DH6, we try to systematically derive all of the interactions that are allowed by this symmetry in this model. And first, let me introduce the interactions that are living on these dimers. So I will call these dumbbells the dimers, and everything else is just going to be the bond. So the interdimer interactions, among the interdimer interactions, we can have something like an XXZ type of interaction. So the X and the Y components are the same, but the Z component can be different in this Heisenberg type of XXZ type of interaction. And we can also have a so-called nematic type of interaction. And the nematic may be not the best name, but we chose nematic for describing these interactions. So this is actually a symmetric exchange on isotropy. And these Q operators, they're just quadrupole operators that are defined on these dimers. So the J index, it runs through the dimers here, and 1 and 2, they correspond to the top and the bottom layer in this dumbbell. So we have these quadrupole operators, and this perpendicular here, it just means that these are the quadrupoles that involve the in-plane spin components, so the SX and the SY component. And then we have these symmetric combinations of these SX and SY operators for this dumbbell here.
So can I ask a couple quick questions here?
Yes, please.
So
yes.
like the motivation for this particular Hamiltonian. So I guess the first part, the XXC, is that chosen for like ease of analysis? I mean, are you going to take like a small J perp limit or something like that?
Yes.
Or...
Yeah. So we didn't have anything in mind, like what, okay, so of course, if you have a very, a Hamiltonian that contains many, many terms, then a lot of things can happen depending on the values of those terms with respect to each other. And we didn't really investigate any, limiting cases for this and see what would be the ground state and the excitation spectrum. That's something that one can do. Why we are doing this, starting from the symmetry analysis, is because we would like to collect all of the terms that are present, that are allowed by the symmetry. Because, if you take a magnet, when an interaction is symmetry allowed, then it will be there, even if it's very small. And most of the time we neglect the really small ones when we try to characterize the material. But when it comes to the, discussing the topology of these bands, even a very small anisotropic term can actually destroy, the band topology. And this is what I would like to show later. So we don't really consider actually the size of these interactions with respect to each other. We just want to devise the most general Hamiltonian that one can have for the bilayer Kagome system.
Okay, and then the other physics that I wanted to ask about is that pneumatic term. I mean, so is that bringing in something new?
It will. I can promise. It will. In the case, if I was just looking at the, so these pneumatic terms, these are, usually if you look at the magnet, it's just like the Jarzynski Mori, I would say. Instead of having this anti-symmetric exchange just as the Jarzynski Mori interaction, this is the symmetric exchange on isotropy. So this is very, very small. It's like 100 times smaller than everything else in the Hamiltonian usually, or even smaller than that. And looking at the magnetic excitations, or in this case, the triplet excitations, they would not have a huge effect on how the bands look, but they will have a very huge effect on the topology of these bands. So that's why we are trying to take this into account, this and everything else that is still allowed by the symmetry. This is just a purely, let's say, has a purely mathematical motivation to say like, what does the symmetry, what does the point group symmetry allow for me to have in this Hamiltonian, and I will just put everything in there. and then try to analyze the effects of these different terms in the bands of these triplets.
Mm-hmm. But if I understood what you said, the pneumatic term is important for changing the band topology. It plays the role of like the DM terms in the previous example.
We will have this and the DM as well. So the DM
also, okay.
Yes. So they have a different role, but I will talk about that in details.
Okay. All right. Great. Thank you.
Thank you so much for the questions. Yeah. So these are the only interactions that we can have for the dimers, because the dimer is an inversion center. It cannot have Jarzynski moria, but we can have DM interaction on the bonds here that are connecting the dimers. So the first neighbor interactions, I call them first neighbor because they're first neighbor between the dimers. So this first neighbor, it also can have this XXZ anisotropy, and it can have Jarzynski moria, and the D vector now has in-plane and out-of-plane components. And what I would like to point out here is that the in-plane component, these are perpendicular to these bonds, but the in-plane component, it has opposite sign in the top and the bottom layer. And that means that when we write up this bond wave formalism and a Hamiltonian for the triplets, these actually will cancel in the linear order, so they will not matter at all. But what will remain is the out of plane, so the DZ component of this Jarzynski moria interaction that is uniform in the top and the bottom layer. And we also take into account the second neighbor Jarzynski, but just because, so it doesn't really change much, but we would like to map out kind of a phase diagram for these non-trivial bands, and how as a function of the D and the D prime and the D double prime, so the first and the second neighbor Jarzynski moria, and to see like if we can tune a band touching topological transition between these triplets. And then we have pneumatic interactions, both in plane and out of plane for these first neighbor bonds. So the in plane components, again, they contain the X and the Y components of the spins, and the out of plane components, they are made of the ZX and the YZ, the symmetric combination of these operators. And that's all. And of course, we could have, we could go to second neighbor and third neighbor and so on interactions and classify all of them. But at the end, when you put these terms together, what will happen is that these further neighbors, they will just renormalize, so to speak, these coefficients in front of these different terms, and they won't really be very important in terms of how they change the topology, or whether that will be affected or not. So we will stop right here, and these are going to be the terms that we are going to investigate. And this is just a schematic figure, sorry, of these quadrupolar or pneumatic interactions on the dimer. So the parallel component, the in-plane component, is uniform in the top and bottom layer. So this is going to survive in linear order, while the out-of-plane component is going to be cancelled because they have opposite signs in the top and the bottom layer. Okay, so I know that was very technical, and I apologize for that. I will not show any horrid things, or hopefully not very many of them. So these are
can I just ask a question about that technical point? So you showed these like p-type orbitals. I mean, I'm not sure I understood.
Yeah, because I'm not showing it very nicely here. So
I mean, I understand that I think the black and the white are supposed to indicate opposite sign. Sorry, the white and the green are supposed to indicate different signs. So that's why there's a cancellation on the figure C versus figure A. But what is that p-type orbital?
It's not p-type. It's my bad illustration of what happens here. So that's again a very good question. So these quadruples, they transform the same way as the d orbitals, in fact, and these are just parts of the d orbitals that I show. So one could if I was not very lazy, I would have drawn here a proper d orbital, and these green parts would have a white part that is perpendicular to it, like that. I don't know whether you can see how.
Yeah, I can see. Yeah.
Yeah, and then here as well, right? So but I missed them because I felt like this already shows kind of this the symmetry, how I go around these different bonds, and here it would be the same. So for example, the bond that I have here, this one, this is actually just the qx square minus y square. So like I just represent it with the d orbital, that is the dx squared minus y squared, because they transform the same way. And then it would have a lobe here, perpendicular, a white lobe that's perpendicular to the green one. And these ones are the yz and the xz orbitals, or the dyz and the dxz, and they would live in a plane that is perpendicular to this slide. Say this one would be, for example, the yz plane that I'm showing, and from the top, this is how the d orbital looks like. So it would have this white lobe here, and then a green lobe next to it, and then a white below this green, and another green below this white, which is not seen from the top view. It's horrible. I think I have a slide where I showed it. Let me try to find it. Yeah, I have
those orbitals are coming from.
Hidden slide.
Yes, right. No, I think it's clear. I see. Okay, so this is the Q.
Yeah.
Okay.
Yes. So this is just like how I could represent, say, this Q term. Instead of having a vector like what I have for the Gaussian schemoria, one can represent it with the vector. I can maybe represent it with these orbitals, or some analog with the d orbitals. And from this, I only leave the green lobes and not the white ones.
Mm-hmm.
And then here for the yz and the zx, from the top view, I only see the white or the green, which are these ones. I'm sorry for this. It's a very elaborate. Maybe.
Okay. No, it's clear enough to me. So I'm happy.
Okay.
Thank you.
Thank you very much for the question. Okay, so these are the different interactions that we can have. So there is something that this was the xxz, but for simplicity, we're usually going to consider it as a Heisenberg. So we're going to set the j parallel and perpendicular to be the same. And then we have the antisymmetric exchange, which is the Gaussian schemoria, and the symmetric exchange on anisotropy, which is the pneumatic interaction. And also we can have a magnetic field. And of those, we are just going to consider the one where the direction of this field is along the z-axis, so perpendicular to the plane of this bilayer Kagome. And why we want to consider this is because this one will not break the U1 symmetry. So this is what happens. So, if I just have the Heisenberg Hamiltonian that has a full rotation symmetry, so it has the full SU2 symmetry of the system. And then if I, lower this symmetry by switching on the Gaussian schemoria interaction, then this full rotation symmetry is lower to just this U1 rotation. And then the pneumatic interaction is going to mix the spin component. So SZ is not going to be a good quantum number anymore. And this is going to break the U1 symmetry. And the Zeeman can break the time reversal, which is a symmetry of all of the Hamiltonian before the Zeeman term. So as I said, we are just going to consider the case when the ground state is a dimer singlet covering of this lattice. And we have these singlets, and of course the triplet excitations that can then hop around this lattice, and we would like to write up a kind of like a Hamiltonian for these triplets. And in linear bond wave theory, this is what it looks like. It looks very ugly, but it really isn't, I promise. So we have 9 different excitations because we have A, B, and C dimers in one unit cell. So we have these 3 orbital degrees of freedom, and we have also 3 spin degrees of freedom, 1, 0, or -1 for these triplets. So that gives us 9 different bands in this model. And as it turns out, as long as we just consider linear bond wave formalism and we don't go to higher orders, and we just have Z component of the magnetic field, and there is no in-plane magnetic field, then the SZ0 triplet is not going to speak with the spinful triplet. So this subspace is completely decoupled, and we can discuss it, separately from the other 2. And as I said, these T operators, the sigma part, which is the spinful part, it contains the +1 and -1 triplet, and both of these triplet operators, the +1 and the -1, and also the T0, they contain the 3 triplets that correspond to the 3 sublattices or 3 dimers that are in the unit cell. So these are the 9 triplets that we have, and we can write, separately, as I said, the spinful part and the spinless part. So this is going to remain trivial in most of the cases because neither of these interactions actually are affecting the T0 triplet. And the spinful part, we're going to rewrite. So we have these M matrices, which is most of the time I'm just going to talk about that M matrix, which is practically the hopping Hamiltonian of these triplet excitations. And I will neglect the pairing terms, the T dagger, and the TT terms. So these N matrices. And why I can get away with that is because these M and N matrices, they are similar. So it means that they only differ in their diagonals. So the N is the same as the M matrix, except it has zeros in its diagonal. So the topological properties, if I just concentrate on the M matrix, won't be affected by that. If I forget about the full Bogel-Bodleian Hamiltonian and just concentrate on the hopping part, it's going to be still fine. So we can rewrite both of these matrices in terms of decoupling the spin and the orbital degrees of freedom. So the spin is a 2x2 problem because we have this plus and minus 1 spin, and then the orbital is a 3x3 matrix, or it's going to be described with 3x3 matrices because we have A, B, and C sublattices or dimers in the unit cell. And if I want to write different terms, then what I would like to emphasize is that first, so I will not show the N because the N matrix is the same except the diagonal part. So in the x-axis or the Heisenberg term, we have on the spin in the spin subspace, we just have the identity operator. So this naturally doesn't care about which triplet we are considering. And these lambdas that we also have here, these are just 3 of the real Gell-Mann matrices that will describe what happens with the orbital degrees of freedom in this Kagome lattice. For the Djouraschinsky-Moria, however, we have the SZ in this spin sector, which means that although this is still diagonal and it leaves the SZ as a good quantum number, it will assign a minus, or like a sign difference for the up and the down triplet, so the +1 and -1 triplet. And that is actually this is why we will have this kind of like gap and the non-trivial band topology for the triplets. And then of course we have the Zeeman term, and as long as we only have the Z component, this also is going to it's not going to mix the spin degrees of freedom, and it's just going to split the up and down triplet.
So is there some feature here that is dependent on the Kagame structure, having like the 3-point basis in one of the layers? I mean, if I had a bilayer honeycomb lattice,
yeah,
say with second neighbor interactions,
mm-hmm.
Would I get qualitatively similar things, or is there something special about having the 3 sites in the unit cell in a single layer?
Yeah, so this would be the same in a honeycomb bilayer or any kind of bilayer, right? So the Heisenberg term, by it only, you are asking whether I would have the same identity operators only, and
no, I'm asking about the physics that you're getting at. So does your final topology depend on the Kagame structure? So you wouldn't have it, say, in a bilayer honeycomb? You would have
it in the bilayer honeycomb as well.
Okay.
Yes, it would. The honeycomb would be actually easier, mathematically, because you wouldn't have, instead of the 3x3 matrices and the Gell-Mann matrices.
Yeah, I guess that's kind of what's behind my question. If you needed to go to a more complex lattice in larger matrices, or
no, we didn't. But
okay.
Yes, back when we started working on it, it was not the ultimate goal, but what came out. So actually, we had other motivations behind the Kagome. We wanted to study also this linear touching and the quadratic band touching, and what's the difference between them, which I will very quickly go through here as well. Mm-hmm. But then it turned into something entirely different. But the physics would be the same for the honeycomb as well.
Okay.
And I will very, very briefly talk about that at the end of this presentation.
Okay,
right.
Thanks.
So yeah, thank you. So there is no mixing between the +1 and -1 triplets if we just have this U1 symmetric Hamiltonian. And that starting with the most symmetric case, the SU2 case, or even in this x-axis model, would just have these 3 bands for the SU2 symmetric case, that are threefold degenerate with the spin index. And now if we include the Jaworski-Mole interaction, then that will have, an effect on the +1 and the -1 triplet. So, the red and the purple and these black bands in the bottom, they would be twofold degenerate with the + and -1 indices, but the zero triplet is going to remain unchanged. So this is just, these spin-fold triplet bands separately plotted from this T0 triplet. So they are fully gapped, and they have finite Chern numbers, and they're twofold degenerate with each other. So we have for this U1 symmetric case, when we just have the Jaworski-Mole interaction, the +1 and -1 subspace is also decoupled from each other. So the spins are not mixed, as I showed before. This Hamiltonian, they are completely diagonal in the spin sector. We just have the SZ and the identity operator in them. So we can diagonalize them separately and also compute their Chern numbers separately from each other. And then we can map out, as a function of these Jaworski-Mole interactions, the first neighbor and the second neighbor, something that is like a topological phase diagram, so to speak. So like, this band touching phase diagram, where we have a quadratic touching along this line here, when the first neighbor Jaworski-Mole is the same, but with opposite sign as the second neighbor. And then we can have, and so this quadratic touching, this happens at the gamma point, and the linear touching transition happens at the K and the K prime point, when the value of this, the first neighbor Jaworski-Mole is 2 times the second neighbor Jaworski-Mole. And one can get these lines, these transition lines. So when this mass term in this Hamiltonian becomes 0 analytically, just by looking at this, just examining this last term, when this is going to vanish, and when it's finite. And if we now expand, so if we wanted to characterize this quadratic and linear band touching transition, then we can kind of expand the model around these touching points and come up with some kind of an effective Hamiltonian that looks very similar to this generic Dirac model, what we usually discuss, that only contains these 2 bands. So now we have just the Pauli matrices that correspond to these, this orbital, or like these 2 bands that are touching at the gamma point or the K point. And then the D vector is going to contain everything that we need to know about the topology of these bands, and we can compute the Berry curvature using the components of this D vector. That is kind of like a pseudomagnetic field that splits these 2 levels. And one can also compute the Chern number, or like in the vicinity, at least, the contribution of this Berry curvature in the vicinity of these points where we expand about. And I will not, I think I will be faster here at this point, because this is not the main point of the talk. But I just wanted to show that one can really analyze these different band touching transitions, and the expansion about the K point is going to give us a Hamiltonian that has this form, and the Kx and the Ky now, they're measured from the K point. And the dz is going to vanish when we are at this boundary for this linear band touching transition. And we can compute the Berry curvature using this effective Hamiltonian for these 2 bands, for the top band and the middle band, that will participate in this band touching transition. And the K0 here is just it's an artificial parameter that we introduce for having a nicer form. As you can see, this is going to go to 0 for when we are at the transition point. And when we integrate this, in the vicinity around the disk, in the vicinity of this K point, then the Chern number that comes, from that part is going to be just this m/2, because this part is going to go to 0 as we approach this line, and then we just have either +1/2 or -1/2, depending on whether we are in the + or -1 triplet band, or whether we are on one side or the other side of this transition. So the change of this topological charge across this band touching is going to be 1, and the total change is going to be 2, because we have 2 of these points in the brilliance, also the K and the K prime point, and the K prime point behaves exactly the same way. So the linear touching is just going to give us half of this topological charge, so that it is related to the winding around this point. And what we wanted to select, so this, of course, the Berry curvature. So if we plot this density of the Berry curvature, it has the maximum at these key points. And if we look at now the quadratic band touching, that's going to be a little bit different. So now, of course, we have to go to second order in this expansion, but otherwise one can do the same mathematics. And we have, the Berry curvature again can be expressed just, in terms of these d vectors, and so the d components and the exchange constant, and then we can write up again the Chern number, the contribution to the Chern number from this from the vicinity of this gamma point, and what this Berry curvature, how this Berry curvature is distributed, is not centered at the gamma point, but is centered around the ring, around this point on both bands. Unfortunately, this band it doesn't show, but it actually is a ring on both sides. And then as we go closer and closer to this touching point here, the radius of this ring is going to be smaller and smaller, and when they touch, they actually are just concentrated at that point. And here the binding is 2, and we have this the change in the Chern number locally here is just going to be 2. So the full change is coming from this quadratic touching transition. And this is just to show how this Berry curvature looks like if we go away from the gamma point. So it has a maximum at a given value. So it actually looks like it's on a ring. So this is just the radial the distance from this gamma point for the Berry curvature. Put it here in this figure. Okay, so so much about the quadratic at the inner touching points. And I was talking about the Chern number of these bands, and you could very well ask, so now the plus and minus 1 triplets, they're degenerate, and they have opposite Chern numbers. So the Chern number is really not the topological index that we need, but it actually will be if we turn on the magnetic field and we Zeeman split the triplet excitation. So in that case, this is exactly what happens. So this is the band structure. We have these 3 triplets that are split by the magnetic field, and the Chern numbers are opposite for the minus 1 and the plus 1 triplet excitations. So this is what would happen if you have large enough magnetic field that can fully separate or like fully split these triplet excitations. And then the Chern numbers may not cancel, and we have these Chern full bands, and most probably something like a thermal Hall conductivity as an indication for this non-trivial band topology. But let's go back to the part when the magnetic field is 0. And then, instead of the Chern number, what we can define is the Z2 index, which is in this case when we just have this U1 symmetric Hamiltonian, is just going to be the spin Chern number, which is just this staggered combination of the Chern number for the up and the down triplet. And then if we plot the spectrum compute the spectrum for an open geometry, of course we will find these twofold degenerate or 2 edge modes on both sides with up and down spins that travel in opposite directions. So the question here now is really that what happens if I add the pneumatic interaction? So this pneumatic interaction seems to be something similar to the Rashba term in the original model, because it has Sx and Sy components in the spin sector. So if I decouple again my pneumatic term for the spin and orbital parts, then in the spin part now I mix the up and down triplet. So this is formally it looks similar to the Rashba term, and then one can ask the question: so does it behave as the Rashba term for these magnetic excitations or not? And the simplest way to actually see is kind of set a value for this k and plot this open geometry, and then see whether it actually will survive or not. And unfortunately, it doesn't. So what we see here is that whenever we have a pneumatic interaction, these edge modes in the open geometry, they become trivial and they don't cross anymore. So it not only just hybridizes these plus and minus 1 triplets, but it also will apparently kill out the Z2 topology. And
can I ask? So
yes,
this is okay. Maybe you're going to answer it. So I was going to ask, there must be a symmetry change or something with these.
That's right. Exactly. Exactly. So yeah, of course, two things could happen, right? So one thing is that maybe I chose a K that is too large, and maybe there was a band touching transition here, which took us to the trivial phase. And this is always a possibility. So one should be more strict. But one can study like where does these two bands close, and just take a K value that is smaller, which is what we did. So it's actually destroying the Z2 topology. But one can be more strict and then see, so what's the effect of this pneumatic interaction really? And this is what I'm going to do here. So we can also devise this pseudo time reversal operator that will square to -1, and it can formally take the role of the time reversal operator, or that was the time reversal operator for the electrons. And this is a symmetry. This pseudo time reversal symmetry is a symmetry that has the potential to save this Z2 topology. And how one can actually write this up is practically a U1, the U1 symmetry times the original physical time reversal symmetry. So the physical time reversal operator for the triplets is this 2x2 identity matrix. Please disregard it; it's not so very important. This is just connecting it's just describing this particle hole space. And what really matters, what I was, the formalism, what I was talking about this problem is that we have this spin part here, this 2x2 part, which is the up and down triplet, and then the orbital part, which is just a 3x3 identity matrix in these cases. So the time reversal operator acts on the triplets, the up and down triplets, in a way that it will exchange the up triplet with the +1 triplet with the -1 triplet, so the sigma x polymatrix, and times the complex conjugation. And time reversal operator doesn't care about the sublattices, so then that's just going to be an identity operator in the orbital subspace. And U1 rotation around the z-axis is generated by the sigma z polymatrix, so that we can write up as a sigma z cross. Again, the orbital degrees of freedom are not affected by this. And it is very easy to see, that these different terms in our Hamiltonian, how they would behave under these different, whether they are invariant or not invariant under these different symmetries. And one can show easily that the xxz and the dm, they are U1 symmetric, and also the z component of the magnetic field. But the pneumatic interaction will mix the up and down triplets, so they will break this U1 symmetry. And also one can show that they, of course, this x and the z, they want to commute with each other. And with the physical time reversal, everybody's time reversal is symmetric, right? Because one would naturally, from just a spin model, expect that these terms are time reversal symmetric, but also one can see, the form of this time reversal operator and the forms of these operators here, that whenever, say, I act, for example, on the dm interaction, then what will happen with this sigma z, and what will happen with these Pauli matrices? Oh, sorry, not Pauli, the gamma matrices. So in the dm we have the imaginary gamma matrices, which will change sign under this T operator, but so does the sigma z. So this will actually be invariant, and so on. And one can look at all of these terms and discuss whether they change sign or not, or whether they break this physical time reversal or not. And then for the pseudo time reversal operator, I'll just consider this part, and one can show that when we act with this operator on something that is contained, that we have in the xxz model, so that's kind of like an identity operator for the spins, and the gamma matrices for the orbital degrees of freedom. The only effect that this will have is to put a complex conjugation for the orbitals. So for the xxz we have the real gamma matrices, so these are going to be definitely invariant under this pseudo time reversal symmetry. And then we can look at what happens if you have some kind of a Pauli matrix here, and nothing is affecting the orbitals, which is something that a magnetic field would do, and that will actually just change sign. So this will definitely break the pseudo time reversal symmetry. And one can also investigate these other terms where we have some kind of a Pauli matrix coupled to a gamma matrix. And what will happen with this is that the Pauli matrix will have a sign change, and also the gamma matrices will acquire complex conjugation. So this will only be invariant whenever we have the gamma matrices that are imaginary. So the DM is going to be invariant, but the nematic interaction will break this symmetry. So this is the reason why the topology is changed when we have this nematic interaction, because this nematic interaction is kind of like the magnetic field in the original Kane and Mele model. When I turn it on, then the symmetry that was protecting the Z2 topology is not a symmetry of the system anymore. So when the nematic interaction is finite, then the symmetry that could protect the Z2 topology is not a symmetry of the system anymore, because this nematic interaction and the pseudo-TR operator, they don't commute with each other. So that will destroy the Z2 band topology. So anyway, I would like to kind of sum up all of this. But I was trying to convince you about this, that one can have interesting non-trivial band topology for magnetic excitations that are, usually considered as, conventional spin waves and things like that. But we can have, due to larger local Hilbert space, we can have spin degrees of freedom, say, for example, for triplets or for larger spins. And they maybe have a chance to realize a fragile Z2 band topology, similar to the Kane and Mele model. But whenever symmetric exchange anisotropies are allowed by the symmetry of this system and they are present, then they will actually break this pseudo-TR operator that can protect the Z2 topology. And this actually can be present in other systems as well. Say, for example, if we had triplets and bilayer honeycomb lattice, then this is what the spectrum would look like for zero nematic interactions. But if we have finite nematic interactions, then we would have a splitting again in these within these edge modes. And the story is exactly the same. We would have something similar, except a 3x3 matrix. We had a 2x2 matrix here, but it would look very, very, very similar otherwise. And this is also affecting previous works on magnons, when we have bilayers without strong coupling between the layers, and instead of having singlets, we can have these ordered antiferromagnetic or like antiferromagnetically ordered ferromagnetic layers. And there also, if you have nematic interactions, one can see whether they commute with this operator or not, or whether this is really a symmetry of the system or not. And that's kind of unfortunate in the sense that if you have a magnet, then these anisotropies, no matter how small they can be present, and they can very much destroy the Z2 band topology for this system. So further investigation, I think, is probably needed if there are other systems where different kind of symmetries maybe can present or protect this Z2 band topology. And some other open question is so what happens if you have different, maybe some kind of like a local or an internal symmetry of a system, because we have maybe something like a large spin or spin orbital object that is of which the magnet is built off. Or what happens if you have decay and interaction between these triplet excitations and so on. So there are a lot of other things that one can still investigate. And with that, I would like to thank you for your attention, and also wish you happy holidays. And I hope it wasn't very long.
Thank you very much, Judit. Very nice talk.
Thanks.
Okay, are there questions from the audience?
Can I ask a quick question, Greg?
Yeah, please go ahead.
Okay. First, thank you for this very nice presentation. That was very clear and with a lot of detail. So it was more easy to follow. So I have actually two different questions. So the first one is very simple. I did not hear you mentioning about dipole interaction between different spins. So was that included in some, or by some of the other terms that you presented here?
No dipole.
Why is that?
Because in this toy model, we just wanted to see what happens when you have these strongly interacting systems where you just have a Hamiltonian that is written in spin terms, and not say I don't know, dipole interactions that would be maybe more relevant for heavier, I don't know, F-fraction systems and so on.
And do you have any guess on how this dipole-dipole interaction would change all the features that you described today?
It's a good question. I unfortunately don't know.
Okay, perfect. And the other question that I have, it's let me think how to elaborate that more. But usually when we talk about topology, we always refer and we always deal with the block Hamiltonian, right? The Hamiltonian for the block bands, not the Hamiltonian for the Schrödinger equation, if you will, even though we're talking about bosons here. So it's the Hamiltonian. So you remove the exponential to the ik dot r. So it's always this this, let's call block Hamiltonian. So this is how people call this Hamiltonian. And I'm not sure if I understood how you went from the complete Hamiltonian from the Hamiltonian and the spin on the Hamiltonian on the Britain on the block functions.
Yes. So formally, when you write up the linear spin wave theory for magnetic excitations as these ones, for example, you would get very similar Hoping Hamiltonians for different neighboring sites as you would have for a non-interacting electron system. And then, of course, that would formally look very similar, and you could call them block.
Yes, but there's some subtleties, but there are a lot of subtleties here, because if you calculate your Heisenberg equations of motion, now instead of fermion creation and annihilation operator, you have bosons. So right. This makes your Hamiltonian to be, so there's a appearance, and this, I think that the Shin Doyle, which is the first PRB of 2013, he talks about that stuff, which is if you now obtain your block Hamiltonian, then you're going to see the appearance of a sigma 3. And by the sigma 3, they means it's plus in the electron space, not electron, but it's plus on this particle space and minus 1 in the antiparticle space. And when you this type, well, when you have this type of equation, all of a sudden your Bogoliubov-Dejenes needs to be diagonalized using a para-unitary matrix rather than a unitary matrix.
That's exactly right.
Yes, and I remember that there's also some paper by the Japanese guys talking about that Bogoliubov-Dejenes Hamiltonian. The proper way to calculate topological index is not by using a Hermitian Hamiltonian, because actually the block Hamiltonian of magnons, it's non-Hermitian.
That's exactly right. So this is a subtlety that when you compute the Chern number, for example, let me come back. I don't know whether I show the Chern number. Here, you compute these overlaps, right? So you have your n's are your eigenvalues. So when you solve the linear spin wave Hamiltonian, as you said, you use a Bogoliubov-Dejenes.
Exactly.
You have a Bogoliubov-Dejenes type of a problem, so you use Bogoliubov transformation. And when you compute this overlap, the scalar product is not as simple as you can see it here. Yes. But you would put here that sigma z, kind of sigma z, where you have the plus ones and the minus ones in the diagonal. So it's kind of the metric has changed, but other than that, nothing really, nothing else really does.
Okay, so
you can import, all of these formulas, but one has to, of course, as you say, be very careful that I have now a mixture of the creation and annihilation operators. So I can just, compute these scalar products the way that I would normally do, for if I just had a Hoping Hamiltonian kind of, but I also need to be careful that
okay, so I see. Okay, so in principle, you have used this, set of this nuance about the non-Hermitian, even though you didn't talk about that during the talk.
Yeah, of course.
Okay, awesome.
I'm sorry for not mentioning that. I felt like that's too technical and too
much. Oh yes, I agree completely. Yeah. Yeah. Okay. Perfect. Thank you very much, Judit. Thank you very much. Yeah, nice talk.
So I think Noah has his hand up. Go ahead, Noah.
Cold atoms. It seems maybe we can enforce the theta, this pseudo time reversal symmetry, with a cold atom setup somehow, or at least maybe, I guess you could call it fine tuning. We can fine tune it away perhaps in a cold atom context.
That's
Maybe,
right.
I wonder what in that case, how would we read out this Chern number, or this spin Chern number kind of thing in the cold atom context?
Okay, I'm not familiar with quad atom context, but I guess with quad atoms, you can do almost anything. And that means that you can engineer your model in a way that you don't have the, the not so glorious pneumatic interaction.
Okay, so suppose you do that, then how do you read it out is the question.
How do you read out? You mean the
Like,
non-trivial band topology?
Yeah.
Whether you have Z2 or not Z2? I'm not sure how one would measure, for example, Nernst effect or
Exactly.
space potential for the quad atoms.
Well, we can do time of flight. We can let
Very
the trap
good.
go and make an image. So maybe I should put the card on the table. So with Ian, about 10 years ago, we thought about the simplest topological insulator. We thought about like quantum Hall fluid. But Ian asked me, like, suppose I go do whatever Judit tells me to do and I get a Chern number. How can I read it out? We were thinking about fermions, non-interacting, Chern number 1, or Chern number 2. And the answer that we came up with was just let the atoms go and then look at what they call time of flight. It becomes a momentum distribution. They take a picture. They take an absorption image, but after you let them expand, it's like a momentum distribution. What we found was if it's Chern number 3, you get 3 bumps.
Oh, cool.
Time of flight. But if it's Chern number -3, you also get 3 bumps. Eduardo Fradkin pointed that out. So it's the absolute value of the Chern number, not the Chern number itself. But that's pretty good. In the case of this bosons, because actually they like bosons, the cold atom guys. Fermions, they don't live very long, and when they do these kind of cold atom, to get it to be like a Chern number, you need like some tricks, and those tricks don't work for fermions. It turns out the fermions that they usually use, but they do work for bosons. So okay, so you have bosons. They like bosons. You got a flat band, and then you got these fancy bands above it with the Chern number non-zero. And so the question then is, how do we read it out? My guess would be you do some kind of time of flight, but it'd have to be kind of, I guess, spin resolved or something, because the total Chern number is 0, you're saying, for the simplest case, right?
For this one, yes. You can test it if you have magnetic field, you split them, then the Chern number will be finite. Field. And then you can probably do the same measurement as you would do.
But if we don't split it, the simplest case, without the big Zeeman field,
then the Chern number is
0. Okay, we'll think about it. Maybe there's a way to do it.
That would be great. I guess with artificial systems like these magnetic crystals and so on, one can devise it in a way that you don't have certain interactions or certain anisotropies like this pneumatic one, and then we stand a chance to design systems where you can have the Z2 topology. Thanks for the question.
Great. Any other questions? Okay, if not, thanks very much, Judit, again, for a very nice, engaging talk. I certainly learned a number of things. And
thank you so much for the questions and for allowing me to, present our work here. Thank you so much.
Hopefully we'll meet in person at some point.
That would be great. That would be very nice. If you can come over, it would be very nice to welcome you here.
Yeah, no, it'd be great to meet in person.
Yeah, that would be nice.
Okay.
Thank you.
All right. Thanks, everyone.
Thanks. Have a
happy holidays to all.
Yes. Happy holidays.